Good morning and welcome to this first lecture on fundamentals of acoustics. So today we will start looking at a spring mass damper system. The objective being one, of course, just to review basic vibrations, and the other main objective is to introduce the idea of mechanical impedance. Okay. So here we have a spring mass damper system . In keeping with the notation with the book by Kinsler and Frey, I will use S for a spring, okay, and R for the damper and M for the mass. Okay. Now the equation of motion for this system is mx double dot plus rx dot plus sx is equal to f e to the power of j omega t. And the homogeneous solution, so we will look at the solution now, okay, which will be composed of two parts. Okay. One part is the complementary solution, and then the other is the particular integral. So the complementary solution comes from the homogeneous equation mx double dot plus rx dot plus sx equal to 0. Okay. Now we substitute x of t as some amplitude times e to the power gamma t. We substitute this assumed solution over here, okay, so that we get x dot of t is equal to a gamma e to the power gamma t, and x double dot of t is equal to a gamma square e to the power of gamma t. If we substitute this into this equation, the homogeneous equation, we get m gamma square a e to the power of gamma t plus r a gamma e to the power gamma t plus s a e to the power gamma t is equal to 0, and a e to the power gamma t of course cannot be 0 because then my solution is a trivial solution. So this part is not 0, okay, so I will remove it. So that I am left with m gamma square plus r gamma plus s equal to 0. As a quadratic in gamma, so that we get gamma 1 comma 2 solutions as minus r plus minus square root of r square minus 4 ms by twice m. Now this can be written as minus r by twice m plus or minus square root of r by 2m whole squared minus s over m. Now if we set r by twice m is equal to the damping coefficient times the natural frequency omega n, okay. So then what we will get is is xi to square root of s over m, where omega n is square root of s over m, and therefore the xi is given by r by 2 square root of s m. And if we bring this back into this equation, what we will have over here is minus xi omega n plus or minus square root of xi square omega n square minus omega n square, and if I take out the omega n, I have minus xi omega n plus minus omega n square root of xi square minus 1, and typically this xi is much smaller than 1, and therefore we say minus xi omega n plus minus I omega n square root of 1 minus xi square. So these are the two roots of this quadratic, okay. And so the complementary solution, okay, where we set the forcing to 0, that solution, let me call it x complementary as a1 e to the power gamma 1 t, where gamma 1 is one of these gammas, and plus a2 e to the power gamma 2 t, where gamma 2 is the second of the two roots, okay. That is one part. Then we have to go for the particular solution. Okay. Now because this is a linear system, it's a linear system driven by a forcing at a single frequency, the system will respond at the same frequency. So I can write the particular solution as some capital X tilde, tilde implies it can be complex, e to the power of j omega t, okay. Now if we substitute this back into the inhomogeneous equation that is driven by a force, we substitute it back, what we get is minus omega square m x tilde e to the power of j omega t plus j omega r x tilde e to the power of j omega t plus x s x tilde e to the power of j omega t is equal to f e to the power j omega t. Okay. Here I am assuming that this f is real, which is okay because everything begins with f, whereas I am saying that this x tilde can be complex. Now if we eliminate e to the power j omega t because it is not 0, so I can divide the whole equation by e to the power j omega t. So this goes, this goes and this goes, and if I collect x tilde and its coefficient separately, minus omega square m plus j omega r plus s is equal to f. So this x is my, x tilde is what I want to know, it is my unknown. Therefore this x tilde is equal to f divided by minus omega square m plus j omega r plus s. Okay. So that my particular solution now is minus f bar, sorry, f by minus omega square m plus j omega r plus s into e to the power of j omega t. Okay. So now I have the complementary solution and I have the particular integral. So the total solution is the sum of these two, x c of t plus x p of t. So let us do that. Let us do that here. So the total solution is given by x c of t plus x p of t is equal to a1 e to the power gamma 1 t plus a2 e to the power of gamma 2 t plus f by minus omega square m plus j omega r plus s e to the power j omega t. Okay. Now if you recall, this was a1 e to the power of, let us say, minus xi omega n plus I omega n square root of 1 minus xi square into t plus a2 e to the power of minus xi omega n minus I omega n square root of 1 minus xi square into t plus this particular integral f by e to the power j omega t. Okay. This can be further simplified. I take e to the power of minus xi omega n t as common, and then I have a1 e to the power of minus I omega dt plus plus a2 e to the power of minus I omega dt plus f over s. Okay. So this is the transient part or the complementary part. That comes because of the initial conditions, and this is the particular integral. Now as time goes to infinity, so now this is the total solution, let me call it this is a total solution. Okay. And if you subject it to initial conditions which are x t at time t equal to 0 is, let us say, x0, and x dot total at time equal to 0 is, let us say, x dot 0. Okay. Then using these two we can find the constants, the unknown constants a1 and a2. They can turn out complex. Okay, they can turn out to be complex. Okay. So now you have the total solution. Okay, that's one thing, how to get the total solution. Total solution. Okay. Now I am of course assuming a familiarity with vibrations, and therefore I have proceeded straight away using the complex notation. So the advantage of the complex notation okay, one is that the derivatives simplify. Okay. So derivatives simplify. Okay. I have something, let us say x is some capital X e to the power j omega t, then the derivative is just you bring j omega down, you have x e to the power j omega t, and x double dot similarly j omega square. That is one advantage. The other advantage is that if I force the system using f e to the power j omega t, finally when I have my answer, like here I have my answer. Okay. If I consider the forcing to actual forcing to be f cos omega t, then I just take the real part of the solution, the real part of this solution. Then I get the answer for forcing it using f cos omega t. Similarly, if I consider my forcing to be f sin omega t, then after deriving the total solution, I take the imaginary part of it. Okay, I take the imaginary part of xt of t, and that gives me the response if the forcing was f sin omega t. So I get a dual benefit in one shot. Okay. The only caution is that you have to give the initial conditions, right. That's so if I am choosing f cos omega t to be my forcing and I have to take the real part, then my x0 and x dot 0 should be taken real, which is natural for us, we take them real anyway. However, if you are thinking that the forcing is f sin omega t, and if you want the response, and then you are going to take the imaginary part of the solution, then the initial conditions have to be given in an imaginary manner with an imaginary I in front. Otherwise you will not have the result for the initial conditions. That is a simple caution over here. Okay. That is as far as this total solution is concerned. We have acquired the total solution. Now as time moves forward, as time moves forward, t tends to infinity. Okay, let us say t tends to infinity. xt of t, there is this minus xi omega n t which starts to go to 0. Okay, e to the power minus xi omega n t starts to go to 0, so that this entire term starts to go to 0. So the transient term or the complementary term starts to go to 0. Okay. and what we are left with is this particular integral, which is f e to the power j omega t by minus omega square m plus j omega r plus s. Okay. Now, that is of interest to us. Okay. Most of the time the transient is of little interest to us, transient, okay, because it actually dies away quite quickly or decays away quite quickly. Let us say decays away, decays quickly, and the response is largely due to the forcing, which is this particular integral. Okay. So, my final steady state value, steady state value, steady state response okay, I will keep it as xt only. Steady state response is this f e to the power of j omega t divided by minus omega square m plus j omega r plus s. Okay. Now, there is a lot of information in this bit over here. There is a lot of information in this bit over here. Okay. First of all, we will write it in a slightly different manner. Okay. So, I will multiply by j omega, okay, and as you see, multiplication with j omega results in velocity. This is velocity x dot. Okay. So, now this side is velocity. Okay. Let me call it v t of t. And on the right also I have to multiply with j omega on the top, okay, and this j omega I will take to the denominator and divide by j omega, divide by j omega. As a result, what happens on the right is I have f e to the power of j omega t, and here I have r plus j m omega minus s over omega. Okay. So, that this division by j omega has resulted in this denominator. Okay. Now, this velocity, suppose I keep it, write it as some complex coefficient in front into e to the power of j omega t, and on the right I have f e to the power j omega t by r plus j m omega minus s over omega. Then because e to the power j omega t is not 0, I cancel from both sides. Then my velocity as an amplitude, meaning the coefficient of e to the power j omega t, is given by this force amplitude over this entity. And that entity, let me give it a symbol z tilde m, okay, r plus j m omega minus s over omega. This is called the mechanical impedance. This entity is called the mechanical impedance. So, what is the mechanical impedance? It is the it's the velocity amplitude v tilde, okay, which is the my total Vt of t was some amplitude in front e to the power of j omega t. So, I am referring to the amplitude as in v tilde over here. Okay. Amplitude, I do not mean the modulus, Okay, please do not mistake it for the modulus. By amplitude I mean this coefficient that is there with e to the power j omega t, okay, that is equal to the force amplitude by z tilde mechanical, or this mechanical impedance is the force amplitude by the velocity amplitude at a single frequency, at a single frequency, radian frequency omega. Okay. So, mechanical impedance is the ratio of the force amplitude to the velocity amplitude at a single frequency omega. Okay. So, it is as though we are asking the forcing agent, okay, we are asking the forcing agent how does the system appear to you, how does the system, in this case the spring mass damper system, appear to you, appear to you. And the answer is Z mechanical. It appears to me, or the forcing agent says it appears to me as minus S over omega. Okay. So, as the word impedance implies, the word impedance means what difficulty it poses to me, how difficult is it for me to disturb it or excite it. So, if this value is high, if this value is high, that means the velocity is low, that means the force is largely unable to excite the system. Okay. So, if the impedance is high, the force is unable to disturb it largely. Okay. That is what it means. Now, let us look at the features in here. My mechanical impedance is given by R plus j m omega minus S over omega. So, there are two parts to this in some sense. So, this is the real part, and this is the imaginary part. So, we will call it x. Okay. So, this looks like R plus j x. So, the real part of Z mechanical tilde is R, which represents dissipation. Okay. In this case, dissipation of mechanical energy to heat. Into heat. Okay. Then the imaginary part of Z tilde mechanical is x. Okay. Now, that first of all represents or captures the inertia and stiffness of the system, the non-dissipative aspects of the system, non-dissipative aspects of the system. Okay. For complicated systems, m could be a function of frequency, s could be a function of frequency, and so forth. Because this is a very simple system, m and s are constants over here. Okay. But x, the imaginary part, represents the inertia and stiffness and the non-dissipative part of the system, whereas R represents the dissipative part of the system. The next thing is that if I set the imaginary part of Zm to 0, imaginary part of Z mechanical to 0. If I set it to 0, that means if I set x to 0, okay, then it gives me an equation to compute system resonances. That means if I now set j, m, not j actually, just the imaginary part, which is m omega minus s over omega, if I set it to 0, okay, then my omega n square is s over m, or omega n is equal to plus minus square root of s over m. So it gives me an equation to find the natural frequencies or resonances. Natural frequencies. Now the other aspect is that this impedance, okay, this impedance is intrinsic to the system. Intrinsic to the system. That means it does not depend on forcing. It does not depend on forcing. Okay. Wherever this system is fixed, the system constituting the spring, the damper and the mass, wherever it is fixed in this manner, in this configuration, the impedance it offers is always this, in this manner. So this issue of impedance being intrinsic to the system, details of that we will see in the next class. Thank you.